Okay, thank you, Professor Xie, for your kind introduction. So at first, I would like to thank you, Professor Xie and the organizer community to give me so very important opportunities to attend this wonderful symposium. Okay, so just Professor Zhou and Zhiwei give very wonderful chemistry about the asymmetric catalysis and the photoredox catalysis. So actually, my chemistry also focused on the asymmetric catalysis for the synthesis organ, very powerful, very important, the chiral compound. So just as Professor Zhou share very, very wonderful introduction about the chiral compound, her wide application in the different field, like the chiral drug or the advanced material science. So today, I just show the detailed chemistry from my lab. Okay, so my chemistry mainly focused on to address the highly reactive radical enantioselectivity selectivity control with our developed the Chiral Anionic Ligand combined the couple catalyst. So anyway, so before share my detailed chemistry, I would like to share my my chemistry. So why use our develop this catalyst to address the highly reactive radical enantioselectivity selectivity control. So we want to develop the 3D transition metal combine the chiral anionic ligand. So why to develop this chiral anion ligand? For example, we want to use a couple. The couple is a D9 metal, is a Cap2, actually have good interaction with this radical. So maybe to generate the cation or the anion or the directly undergo radical homogeneous substitution the pathway. So anyway, so you can see in all of these intermediate, the chiral anion can provide the chiral environment. So that means maybe provide the diversity possibilities to realize enantioselectivity selectivity control. Okay, so based on this idea, so in my lab, so maybe in past decade, so we developed different kinds of chiral anion, the ligand, like the phosphate or phosphate combines the neutral ligand. So more recently, we directly use a hybrid, the bidentate or the tridentate anionic ligand, combine the couple. So we want to use this couple 1 as a single electron transfer catalyst to activate different any the neutral substrate to generate a radical. Then couple 1 oxidizes to couple 2. So I just mentioned if generate the couple 2 combine the chiral anionic ligand, so actually have good interaction with this radical, provides the different, very powerful the chiral environment, so maybe to realize the asymmetric transformation. So finally, so we can give to the different kinds of chiral carbon-carbon or the carbon heterobond formations. Okay, so this the chemistry mainly focused on the sp3 carbon-based alkyl radical species. So actually, more recently, like the 3D transition metal, like just the Zhiwei shows the photoredox catalysis or the electrochemistry. So we can use any neutral substrate to generate any different kinds of radical species. So like here, you can see the heteroatom radicals or the very highly reactive sigma type the carbon radicals. So actually, this the radical. So as compared, this the radical have completely the chemical properties. So that means, so maybe it's very difficult to control enantioselectivity. So also more recently, we are very interesting about to address this radical enantioselectivity control. So very lucky, we continue use our developed the catalyst system. So bonding the different the nucleophiles, we can address, like you can see, the highly reactive vinyl radical or the allylyl radical, or even more the heteroatom, the sulfonyl radical, or the SU radical, or the highly reactive cyclopropyl radical enantioselectivity control. Anyway, so more recently we collaborate with Professor Hong Xin for the DFT calculation. We found this radical actually undergo radical homogeneous substitution the pathway. So based on this pathway, more recently we found very interesting reactions. So you can see this reaction, we directly use our developed tridentate anionic ligand bonding the couple, then bonding this different substrate, maybe to generate a couple one their species. So these species have very strong reducing capability, so can activate any neutral substrate to generate different kinds of radical species. Okay, so then CAP1 oxidizes to the CAP2. So actually this CAP2 is a thermodynamic, the favored the species. So then this instituted generated radical directly undergo radical homogeneous substitution the pathway, so then to generate all kinds of chiral building blocks. So you can see in this reaction system, we can tolerate any radical species, like the highly reactive, the primary or secondary or tertiary carbon radical, even more the methyl radicals. So also we can tolerate highly reactive nitrogen or oxygen-based radical species. Also we can tolerate the different, the acyl, sulfonyl, the phosphine, all kinds of radical species. So that means, so based on this strategy, so we can provide a general approach, can tolerate any highly reactive radical species. Okay, so today, because of time limitation, I just show the only one reaction, so cross-coupling reaction. So cross-coupling reaction, so like sp2 So like sp2 electrifies, bonding the nucleophiles to form the carbon-carbon or even more the carbon heterobond formations. So these reactions have wide application in the different fields because can provide very important tool for synthesis of organic compounds. So have wide application like for the synthesis very important the drugs or the advantage the materials. So this reaction have been recognized by many famous name reactions and even more the Nobel Prize. So before mainly focused on the sp2 electrifies. So more recently, scientists want to move to the sp3 electrifies. So like this racemic electrifies, hope to give only one the chiral compound. So because as compared to sp2 electrifies, sp3 electrifies want to realize cross-coupling reaction, so it's not easy. So because sp3 electrifies is very difficult to undergo a fundamental transformation like oxidative addition. So if they realize oxidative addition to generate this intermediate, also easily undergo beta hydrogenation give olefin. Also, it's very difficult to undergo reductive elimination give our design as a product. So that is why this reaction is very challenging. So more recently, some great scientists discovery uses 3D transition metal like the nickel, iron, or the copper catalyst. Because this metal have good single electric reducing capability, maybe directly to activate racemic alkyl electrifies give prochiral radical intermediate. So then, in the presence of chiral ligand, maybe for the hypervalent, the transition metal, or maybe directly undergo radical homogeneous substitution the pathway, then they can realize the chiral carbon-carbon bonds formations. So also, maybe this chemistry undergoes 2 decades. So also made great progress in this field, still remain unsolved the problems. So because this reaction just electrifies and nucleofies, so we can see, like in the case of electrifies, these 2 electrifies is very difficult to realize the transformation. So first one is unfunctional alkyl electrifies, gives this unfunctional alkyl radicals, because this radical is highly reactive. So also is very difficult to realize enantiomer discrimination, because in the presence of 2 similar alkyl groups. So later I will show the detail. So this is the radical, why to realize enantiomer selectivity control very challenging. So another is the tertiary electrifiers give the tertiary radicals, because this is the radical very bulky. Also is very difficult to have good interaction with this transition metal. So on the other hand, in the case of nucleophiles, I just mentioned use nickel, iron, or copper catalyst, mainly focused on the carbon-carbon bonds formation. So it's very difficult to undergo the carbon heterobond formation in the presence of heteroatom nucleophiles. So maybe this metal is preferred to undergo reductionation, so not easy to undergo reductionation. Okay, so I just mentioned our chemistry mainly focused on the couple. So however, before the couple pays less attention, use a catalyst to realize this transformation. So actually couple is very cheap and very low toxicity. So why the couple is very difficult to realize this transformation? So actually it's very easy to understand because couple, as compared this metal like the nickel, cobalt catalyst, so have very weak reducing capability. That means it's very difficult to initiate this reaction. On the other hand, if initiate to generate a radical, so I just mentioned the radical is highly reactive, also it's very difficult to control in non-selectivity. So anyway, so we want to use our developed the carbon catalyst to realize this transformation. So most importantly, we want to use this catalyst to address these challenges or problems, like very challenging electrophiles and very challenging nucleophiles. Okay, so actually the couple I just mentioned, like the couple-2 is a D9 metal, have good interaction with this radical, maybe forms the couple-3 intermediate. So actually, so this couple-3 intermediate is highly reactive, easily undergo reductionation, so to generate the carbon, and even more the carbon heterobond formation. So if in the presence of chiral ligand, maybe also to realize asymmetric transformation. So if we want to use a couple as a catalyst to realize the enantioselective conversion cross-carbonyl reaction is very simple. So maybe to directly increase the reducing capability of the couple to initiate this reaction. So that means maybe to realize cross-carbonyl reaction. Okay, so actually in this field, from the Caltech, the Professor Peters and the Professor Fu collaborate to use a photo. So just Zhiwei mentioned, the photo catalyst is really powerful. So for example, if it's a couple 1 in the presence of the photo to generate excited state the couple species. So these species have very strong reducing capability directly to initiate this reaction to generate radicals, then to realize the carbon-nitrogen bonds formation. So we are wondering, so maybe directly use one simple chiral ligand. So we hope use this ligand to increase the reducing capability of the couple. So maybe can initiate this reaction and the very mild the thermal conditions. Don't need the photo and don't need the electrochemistry. So at the same time, if initiate this reaction, so we hope use this ligand to provide the chiral environment to realize the radical enantioselectivity control. So this is our idea. So anyway, so at the same time, so many research groups so use the same concept to do this chemistry. So because of time limitation, I just show my chemistry. So why we have this idea? So I just mentioned, so in my research group, mainly focused on design Chiral Anionic Ligand. So like you can see this ligand. So this ligand is have the tetraamine and phosphine and anionic amide. So all of atom is electron rich. So that means can increase the electron density. So maybe this species combines the nucleophiles from this intermediate, maybe have very strong reducing capability. Maybe can initiate this reaction and the very mild the thermal conditions. Then maybe use this ligand to realize asymmetric transformations. Okay. So anyway, based on this idea, so in my lab, so maybe in past the 5 years, so we set up the different the chiral anionic ligand library. So you can see this ligand have NNP or NNN or the tridentate or the bidentate ligand. So actually, so this ligand is very easily available. So because this chiral skeleton is very cheap, like the alkanoid derived starting material. So we link like the amide on the sulfur amide. So it's very easy to cross to give this ligand. So also this structure is very easily modified. So that means this ligand is very easily available. So up to now in my lab, maybe have 1,000 ligand. So that means it's very easy to screen the reactions. Okay, so I just mentioned maybe this ligand can increase reducing capability of the couple. So more recently, we isolate the many CAP2 the complex. So we test the reduced potential. So you can see this simple couple reduced potential. So this box ligand, the neutral ligand bonding the couple, the reduced potential. So this of the ligand combines the different nucleophiles reduced potential. So you can see like this the species can move to the minus 1.8 watt. So that means this species have very strong reducing capability. Maybe directly initiate the racemic alkyl electrophiles to generate radical. So indeed, so more recently, we use our developed the tridentate anionic ligand, the library, so bonding the different the nucleophiles to form this intermediate. So I just mentioned this intermediate have very strong reducing capability directly to activate racemic halide and the very mild the thermal conditions like the room temperature. So to generate a radical, maybe form the CAP3 intermediate, maybe directly undergo radical homotic substitution pathway. So then we can realize the different chiral carbon-carbon and even more the carbon-heteral bonds formation. Okay, based on this reaction, so you can see the subscope is really broad. So you can see in this reaction, we can tolerate different the carbon-based the nucleophiles, like SP, SP2, even more SP3 carbon nucleophiles. So also, this reaction can tolerate the different the heteroatom nucleophiles. I just mentioned that using nickel, iron, or copper catalyst is very difficult to realize carbon heteral bond formation. So in our reaction system, it's okay. So electrophiles not only to realize SP secondary radicals, so also we can realize the tertiary radical give the all carbon quaternary the centers. So I just mentioned using nickel and copper catalyst is very difficult to realize tertiary radical gives the quaternary chiral centers. So that means based on this the strategy, we can provide the complementary approach for the like the nickel and copper catalyst. So gives the different kinds of chiral carbon-carbon and even more the carbon heteral bonds formation. Maybe have a potential application for the synthesis of very important the chiral drugs and even more the natural products. Okay, so anyway, so based on this the chemistry, the first step is deprotonation or the transprotonation to give this intermediate. However, so many nucleophiles is very difficult to undergo the deprotonation or transprotonation to generate like the carbon nucleophile the intermediate. So you can see the ammonia or the aliphatic amine. So it's very difficult to undergo deprotonation, give the carbon amines an intermediate. So on the other hand, so this the species have very strong the catalyst coordination properties, so easily cause the catalyst poison. So that means we should to develop the another approach to address this cross-coupling reaction. So more recently, we found very special the electrophiles. So this electrophile you can see the amide. So because amide, as compared like the ammonia or the aliphatic amine, so more acid. So that means the presence of inorganic base easily undergo deprotonation of this amide to generate this intermediate. So then, because I just mentioned the CAP1 bonding our tridentate anionic ligand have very strong reducing capability directly to activate this halide to generate a radical. So then maybe form the CAP3 intermediate. So then here I just use these nucleophiles directly undergo outfield nucleophilic attack of this highly reactive CAP3 intermediate, then to realize the carbon nucleophile the bonds formations. Anyway, so this reaction, so because directly use nucleophiles and go outfield nucleophilic attack, the subscope is really broad. So you can see in this reaction, we can tolerate different kinds of amine nucleophiles. Like I just mentioned, very challenging the ammonia, the aliphatic amine, or very bulky aniline, or the hydrazine. So also in this reaction, we can tolerate very easily available the alcohol, even more very bulky the tertiary alcohol. So also can tolerate phenol, carboxylic acid. So more recently, we found this reaction system directly can tolerate very simple water, or the fluoride as a nucleophiles also to realize the carbon-fluorine bonds formations. So also this reaction can tolerate very bulky and soft the carbon nucleophiles to give carbon-carbon bonds formations. So anyway, so electrophiles you can see also can tolerate the secondary and even more very bulky the tertiary electrophiles is okay. So okay, so next because of time limitation, I just show the only one the detailed examples. So I just mentioned we use these radicals because these radicals have alpha function radicals is relatively stable. So more recently, we also to realize highly alkyl radicals with a directing group. So why to introduce a directing group? So it's very easy to understand because use a directing group can be stabilized as a couple. So that means maybe stabilize these highly reactive alkyl radicals. Then maybe to realize intramolecular transformations. How was this the radical? It's very just the unfunctional alkyl radicals building very simple the alkyl groups. So this radical is really challenging to realize in non-selectivity control. So first, so because this the alkyl radical 2 seminar, so it's very difficult to realize in non-discriminations. So just as Professor Zhou shared the very wonderful, developed the very powerful spiral ligand to realize asymmetric hydrogenation, the very simple ketone, and the imine in the presence of two simple the alkyl groups. So anyway, so that chemistry gives me very, very strong inspirations. Okay, on the other hand, so I just mentioned this the radical as compared like the benzylic radical is highly reactive. So sometimes this reaction really, really fast. So how will we want to realize in non-selectivity control? So we need to the more energy barrier. How is this species highly reactive? So that means it's very difficult to realize the energy barrier. So that means so this the radical is highly reactive to highly reactive and is very difficult to realize in non-selectivity control. So we want to learn the enzyme. So anyway, the enzyme provides the carried the pocket, well-confined carried pocket to realize the like the asymmetric transformation. So we want to learn the enzyme, but not enzyme catalysis. Here we want to design well-confined, but the partial open the carried pocket. So like the truncated core, the shaped the carried pocket. Why to develop this kind of the ligand? So you can see this is open the area. So maybe the small alkyl group located is in this field. The large alkyl group located the outside. So I just mentioned this radical is highly reactive. How to use open carried pocket to stabilize this radical? So this is a very big challenge. So anyway, so more recently, we hope to introduce many aryl group or the alkyl group on this ligand. We hope to, through the non-covalent interaction, like the hydrogen-hydrogen or the hydrogen-pi non-covalent interactions to stabilize this alkyl group. So if okay, so based on this carried, open the carried pocket, so the subscope is really broad. So because this area is really open. So that means not only to tolerate the primary alkyl groups, maybe can tolerate the secondary alkyl groups. So even more maybe can tolerate very, very bulky tertiary alkyl groups. So that means if okay, the subscope is really, really broad. Okay, so anyway, so we at first we test this reaction, the racemic iodine, so use amine we can to realize same bonds across carbon reaction. So at the beginning, we use our previous developed the NMP, the ligand. So how was this reaction efficiency and the enantiomer selectivity is really poor. So we tested the couple concentration. We found in the reaction system, the couple concentration is this very, very low. So that means this the ligand, the solubility is not good in this reaction system. So next, at first, we addressed the reaction efficiency. So finally, we introduced the alkyl group on this the phenol ring. So we tested the couple concentration as compare this, they increased very fast. So that means this the ligand solubility is okay. Then we test this reaction. You can see the reaction efficiency is okay. So that means we can address the solubility. So next, we want to provide the chiral pocket to realize enantiomer selectivity control. So continue based on this the ligand to introduce a phenol ring and many alkyl group to provide the well-confined the chiral pocket. Finally, we can address this reaction with good enantiomer selectivity and good reaction efficiency. So I just mentioned, so if based on this ligand, maybe subscope is really broad. So indeed, so you can see in this reaction system, we can tolerate the primary, and the primary is a highly reactive secondary radical. So you can see this the primary alkyl group. We can tolerate many function group. Also the branched, the secondary, or even more the tertiary, the alkyl group. So I just mentioned maybe this reaction can tolerate the primary and the secondary highly reactive radical species. Indeed, in this reaction, you can see we can tolerate the methyl and the different the cyclic and acyclic. Also, we can tolerate very challenging the primary and the tertiary, the alkyl groups. So that means this subscope is really broad. So also this reaction, we can tolerate very similar the alkyl groups, so ethyl and propyl. So very, very similar. So in this reaction system, still gives a good enantiomer selectivity control. Anyway, so up to now, the enantiomer selectivity is not good. We continue to modify this the ligand, hope to address this the problem. So also this reaction can tolerate the secondary highly reactive radical species, also to realize carbon-nitrogen bonds formations. So anyway, so because this is the cyclic amine, so very important. So you can see to generate and go the transformation, give this the building block. So this building block, so then directly give very, very important the chiral drugs. So you can see, so this the building block are many chiral drugs and click the chiral drugs, the motifs. So that means with our strategy easily to synthesize the very important the chiral compounds. Okay. So more recently, we want to use our developed strategy to realize the C bond functionalization. So that means directly from the very simple alkanes, we hope to realize this transformation. So how was this reaction as compare starting material, the racemic iodines? So we addressed the two problems. First problem, we want to realize site selectivity to generate one special radicals. Then we use this the radical, use our developed strategy to realize carbon-nitrogen bonds formations. So anyway, at the beginning, we select these very special alkanes. So because this the hydrogen easily undergo HAT, like in the presence of phenol radical to generate this the radical, then use this our strategy to realize this transformation, to have good yet and good enantiomer selectivity. So how will we directly from the pentane, the hexane, so you can see the site selectivity and the enantiomer selectivity is not good. So we use the racemic iodine to test this reaction, give the C enantiomer selectivity. So that means maybe we continue to modify the ligand, maybe to address this reaction enantiomer selectivity. How to realize the site selectivity? So more recently, we continue to modify the very powerful HAT reagent to realize the site selective HAT to generate one special radical, then maybe to realize the carbon-nitrogen bond formation. So maybe next time to show this the chemistry, the detail. Okay, so also maybe because time limitation, I want to skip this. So next we collaborate with Professor Hong Xin for the DFT calculation. So we want to know how to interaction in COT generated the CAP2 and the radical. So after DFT calculation, so they found so directly undergo radical homogeneous substitution to give the carbon-nitrogen bonds formation. Okay, so maybe I can skip this. Okay, so finally we want to use our developed strategy, hope to synthesize very important the carrier drugs and the natural products. So for example, so we use our developed strategy to synthesize very important the carrier drug and the natural products. So more recently we use this strategy, give the all carbon content receptors. So these centers are many natural products and the carrier drugs motifs. So we use this strategy, we can still divergent synthesis this very important compound. So more recently we collaborate with Professor Haohua Li from the Peking University. He used our developed strategy, give this the building block, because this group and this group easily undergo transformation. So with this strategy, they can divergent the total synthesis of multiple series of natural products. So anyway, so now our ligand is chemistry available. So anyway, so finally I would like to give a brief summary. My chemistry mainly focused to use couple combine the carrier ligand. We can realize different kinds of highly reactive radical species in anti-selective control. So we can realize carbon-carbon and even carbon-hetero and hetero-hetero bond formation. Finally, I would like to thank you, my supervisors and many collaborators and research fellows. Okay, so thank you, the funding support agents. So thank you all for your kind attention.